Hi guys, in this tutorial we're going to look at the ratio test. Now after that we're going to look at 3 examples, which are these. You guys can try them out. Now what is the ratio test and how do we use it? Well, to understand the ratio test, let's assume we have a series an. Now if this is a series, what you want to do is you want to pick two things. One, you want to get an itself, so that is a sub n, and then after that you have from an you have to define a second series, which is basically going to be based on an. But what you're going to do is that we're going to increment wherever there's n, just add 1 there so that you have a sub n plus 1. Now, to use the ratio test, what we do is that we will have to evaluate the limit as n approaches infinity, but this time it's going to be of the ratio, the modulus of the ratio a sub n plus 1, but the ratio to with a sub n itself. So we're going to divide a sub n plus 1 divided by an. Now, to determine whether a sub n converges or diverges, what we'll have to do is we will have to make a comparison of our solution here. When you find your limit, what is the limit? If it turns out that the limit ends up being less than 1, then our conclusion here will be that the an, the expression, the series an, so here we're going to conclude that our series an converges. So this is if our limit here ends up being less than 1. But say after evaluating this limit, we end up finding a solution such that 1, maybe the solution we find is greater than 1, or maybe after evaluating this, we end up getting a solution, or the limit comes out to be equals to infinity. In this case, we will conclude that our an diverges. So this will be the conclusion in this case. And in the final case, say after evaluating the limit, we end up finding that this limit is actually equal to 1. In this case, we will conclude that this test is inconclusive. So this just means that the ratio test has failed. We have to try using different methods to evaluate, to determine whether an converges or diverges. Put in other words, this is a summary of what we have just gone through. So if an is a series with non-zero terms, then we have the 3 cases that are possible. Now, having gone through what the ratio test is, let's look at 3 examples to help us understand what it is really and how to use it. Let's pick the first example. In the first example, we're working with a series, the sum from n equals to 1 to infinity, and then you have 2 power n over n factorial. So let's start with that example. Okay, so in this example, as we saw earlier, we're going to define this as our an. So an here becomes equal to 2 power n over n factorial. Once we have this, the next step will be to determine what our a sub n plus 1 is going to be. So a sub n plus 1, what we're going to do is, in our expression a sub n, where there's n, we're just going to add 1. We're going to have n plus 1 instead. So this becomes 2 to the power n plus 1. Then this will be divided by n plus 1 factorial. So this becomes the expression for a sub n plus 1, while this becomes the expression for a sub n. Once we have the 2 expressions, we can then use the ratio test. Does our an converge or diverge? Well, to answer that question, we have to evaluate the limit as n approaches infinity of the modulus of a sub n, a sub n plus 1, which is just 2 to the power n plus 1, divided by n plus 1 factorial. Then of course divided by, so we're dividing a sub n plus 1 by a sub n, and a sub n is just 2 to the power n divided by n factorial. So of course we have to remember to put the modulus. Now of course here when we change that division symbol to multiplication, what do we get there? So the second term there is just going to interchange. The numerator becomes the denominator. So we're going to have the denominator will become the numerator, n factorial, then 2 to the power n there. Now next up, we're going to use two tricks there. So you have to understand that if you have, let's color this out. So you have to remember that if you have 2 to the power n plus 1, this will have to be the same as 2 to the power n multiplying 2 to the power 1. So of course, when you're multiplying two terms, the base are the same, then you just add their powers with that common base. That is one trick that we're going to use. So we're going to use this and replace this solution or this version where we have that n plus 1. And the next thing we have to deal with that factorial. What I want to do there is I want to compare this n plus 1 factorial to the n factorial there. The bigger one, of course, has to be n plus 1 factorial. So I want to reduce it until when it matches my n plus 1. So here you have to remember that n plus 1 factorial, this will be equal to n plus 1 multiplying n factorial. So I've reached the factorial already. Notice that all I did here was the same expression n plus 1, but now less it by 1. Doing this already gives you a solution of just n there, and since that was what I was looking for, so this is just n factorial. So again, this is what I'll plug in where I have n plus 1 factorial. What happens? So I'll just copy this and let's make the substitutions. So in place of 2 to the power n plus 1, there I will have 2 power n multiplying 2 power 1. And then in place of n plus 1 factorial, here we're going to have n plus 1 multiplying n factorial. So here you see that the n factorial and the n factorial there are going to cancel out. That was our goal. And the 2 to the power n and the 2 to the power n are going to eliminate as well, so that our solution now, or our expression, remains as the limit as n approaches infinity. And then now we have 2 to the power 1, which is just 2 over, and then this is going to be n plus 1. Now what you have to see here is that regardless of what n is, this solution will always be positive, implying that there is no need for us to have the modulus. So this is basically just the limit as n approaches infinity of 2 over n plus 1. Now what you have to see here again is that now you can evaluate what the limit is. As the value of n gets closer to infinity, the solution here will be getting closer and closer to infinity. Not infinity. When the denominator gets to be very, very big, clearly this is going to be approaching 0. So I have to see any number a divided by infinity is just equals to 0. So based on that, here the limit will be equals to 0. Now does an converge or does it diverge? So here we have to see that our limit here as n approach to infinity of a sub n plus 1 divided by a sub n. The solution to this was 0 or is 0, and when you look at 0, 0 is indeed less than 1. So because our solution is less than 1, what is our conclusion? Here we conclude that our series to infinity from n is equals to 1, and then we had, that was n 2 to the power n over n factorial. So that was 2 to the power n over n factorial converges. So remember, to converge, the limit had to be less than 1. So this converges by ratio test. So let's quickly look at the second example. So just like before, first we get what our a sub n is, and in this case we have n squared. Just make sure that it's n squared. So that is, yes, that looks like n squared. Okay, so we have n squared there, then we have 2 power n plus 1. This is over 3 power n. So since this is our n plus 1, our n, our a sub n, next we get a sub n plus 1. So if everywhere where we have n, we put n plus 1, this becomes n plus 1 squared, and then the second term becomes 2 power, where we have n, we'll put n plus 1. Notice that this will be n plus 1, then plus that 1 which is already there. Then this will be to the over 3 power n plus 1. So I want to reduce this a little bit. What do we get? So we can leave this the way it is, or we can expand it. We'll see if we need to expand it later. So n plus 1 to the power 2, and that becomes 2 to the power n plus 2. And then this again is just 3 to the power n plus 1. We can rewrite these two terms using the trick that we used earlier on. This is n plus 1 to the power 2, and then this becomes 2 power n multiplying 2 power 2 there. So of course, common base, so we added the powers there. Of course, that can be taken as a 4. We'll leave it like that for now. Divided by, this will be 3 power n multiplying just 3 there. So this is our a sub n plus 1. Now we can get our limit. So now I want to test. You use the ratio test to perform the test. So we have the limit as n approaches infinity. So here it's the modulus of our a sub n plus 1 is just this term. So we'll just copy it from here, and we'll just plug it here. Now the test says we divide this by a sub n. So our a sub n is this expression here. So this is the division we're performing. Okay, let's just make sure some of these, make them smaller a little bit. Okay, so this is what we have. Okay, so that is done. Now what we have to do here is actually perform the division. So what we have is this. So just change the division to multiplication. Okay, I think I pasted this in the wrong position. So just get this again. I think what I pasted in the wrong position is this expression here. So let me just get this. It's supposed to be here instead of where I have it there. Yeah. So this point was just for a sub n plus 1, not that. So let's just leave it the way it is. So this is the limit that we want to evaluate. So once we reach this part, we want to change the division to multiplication. So when you do that, again, I'll just copy this exactly the way it is. So copy that. Then let's see what we end up with. So the next term, when we change the division to multiplication, they'll change positions. So this is going to end up as 3 to the power n divided by n to the power 2. And then this is going to be 2 to the power n plus 1. So let's see what we have there. So I want a few things to cancel out. Firstly, we see that this 3n and the 3n are going to cancel out. Now, the other thing that I want to eliminate is this 2 to the power n plus 1. How do I get rid of that term? Well, I want to be smart about that part. So we've seen that this term has already cancelled out with that. So now we only have a 1 here. Now I want to find a way of eliminating that 2 to the power n plus 1. I know it eliminates because it can be born from this expression there. So if I take this expression one step back, before we split them like this, you should see that this is the expression which was 2 to the power n plus 2. Now n plus 2 can be rewritten so that it is n plus 1, then plus 1 as well. So that when you add these, it will still give you back that n plus 2. Why am I doing this? So that now I can rewrite this expression, splitting the 2 to the power n plus 1 with the 2 to the power 1. So that now that part can be seen to be, So instead of writing 2 to the power n plus 1, now I can write this as 2 to the power n plus 1 as one term, multiplying 2 to the power 1. Again, notice that when you combine these, you can still end up with 2 to the power n plus 2. This way, now I can eliminate this with this term. Look at what we remain with. Now we have the limit as n approaches infinity. The first part, we have n plus 1 to the power 2. And then you still have that 2 here. This is over 3. And then this is multiplying 1 over n squared. Now again, this term will always be positive regardless of what the value of n is. So I can drop the moduli. This is now just to the infinity. And then I can actually expand that square there. So that in the end, I have 2 multiplying n squared plus 2n plus 1 in the numerator. Then the denominator, I can have 3n squared. From here, to evaluate this limit, we're just going to, you can use L'Hopital, or we can divide every term by n squared. So that if we did that, now this will be the limit to infinity. The 3 can go inside, not the 2 I mean. The 2 can go inside. If we took the 2 inside, this would be 2 n squared divided by n squared, it will be 1. So we'll just remain with the 2 there, plus, and then this will be 4. Then n divided by n squared, so this will be 4 over n. Then next, this will be 2 times that. This is going to be 2. Then 2 divided by n squared. Then in the denominator, I'll do the same thing. 3n squared divided by n squared, so I'll remain with just 3 there. Now, when n approaches infinity, what you have to see is that this term is going to become 0 because the denominator is so big. 4 over infinity is 0. This term will also be 0 here. So that what will remain here as the solution will just be 2 over 3. So that becomes the solution, or the limit in this case. And having found that as the limit, does the expression converge? Does our an converge or diverge? We see that the limit in this case, as n approaches infinity, of our an plus 1 over an, notice that this limit in this case, is it greater than 1 or less than 1? We see this is 2 over 3, and 2 over 3 is also less than 1. Because it is less than 1, we conclude that this our series converges. So it converges. In our last example, we're now going to look at this power series here, and we want to see if this converges or diverges. And we're going to do it by looking at, or by using the ratio test as well. So clearly from here, we can see that our an is going to be the exact expression that we have, which is x plus 3 to the power n over root n. Having defined our an, the next we need our a sub n plus 1. So it's basically the same expression, but where we have n, we'll put n plus 1. So this is going to be x plus 3 to the power n plus 1 over the square root of n plus 1. So this becomes our a n. Now the next part is going to be to bring in the test. So what we want to see is the limit as n approaches infinity, and this is going to be the modulus of our a sub n plus 1, which is just going to be x plus 3. This is to the power n plus 1 divided by root n plus 1. And then this is being divided by our a sub n, which is just x plus 3 to the power n over root n. Now, of course, we have that modulus there. So by the same trick that we saw earlier on, you have to see that when we change this to multiplication, so this is going to be n to infinity, and then this is this can be reduced so that we have x plus 3 to the power n, and then you have x plus 3 to the power 1. This is 2 over root n plus 1. And then this is now going to multiply root n divided by x plus 3 to the power n. You have to see that this again will cancel with that, so that now we have the limit as n approaches infinity. The modulus of this is going to be x plus 3. And then this is, we have that root n here. This is divided by root n plus 1. The x plus 3 here will not be affected by the limit because it doesn't have an n term there. So it's literally just constant there. So I can remove it from that. So you have x plus 3 coming out. And then you also have to see that the modulus will really not be doing anything here. So perhaps let's start with eliminating that modulus. This term will always be positive regardless of what n is. So we're just dealing with this. Then the x plus 3 is constant, not affected by that limit. So we're only going to be working with the n there. So I can have x plus 3 coming out here, and then multiplying the limit as n approaches infinity. And then we have, I'll just put everything under the root. So this is n over n plus 1 there. Okay, so this is what we are evaluating. Now, finally, when you evaluate the limit here as n approaches infinity, by the same trick of dividing everything by n there, you have to see that the limit here is just going to be 1, this part, so that in the end, the limit as n approaches infinity of the modulus of a sub n plus 1 divided by a sub n for our expression where a n was defined earlier. In this case, it's going to give us the expression which is it's going to be equals to x plus 3. So this is going to be the limit. Now this question is actually a power series, and the question was asking us to find the radius of convergence of the power series. So I think I didn't include that part. So the question was sent to me by a student, and a student wanted help with this question. So the question was, find the radius of convergence of the power series. Convergence. So this is of the power series. So in this case, having done that, so we have reduced all this to this by finding the limit, and what we have found is that the limit is going to be equals to this. Now, to test convergence, or to literally get the radius of convergence, we have to remember the definition of the radius of convergence. It says that if we have x plus, so the definition of the radius of convergence is that if you have x here and then minus some term c here, where c is the center of this series, if this is less than 1, then not less than 1, sorry, when this is less than r, then we have then r here will become the radius of convergence. Now if this becomes, let's say, x minus c, in the end we end up with greater than r, then in this case we have the series diverges. Now in this case, what we're looking for is this statement. Notice that this statement here actually does kind of play along with our definition of the ratio test, because from our ratio test, the limit that we have found here, the modulus of this limit has to be less than 1 for the series to converge. In other words, we can literally see this and say x plus 3, its modulus has to be less than 1 for the series to converge. In this case, notice that it then plays along to say that the radius of convergence has to be the 1 equals to 1. So we then conclude that the radius of convergence has to be equals to 1. Okay, now guys, we'll see more of the radius of convergence when we actually do the power series. Alright guys, see you in the next class.